Hey everybody, it's Mr. Francis, and this is my review for Chapter 9. Chapter 9 and 10, now we're going back to compounds, and we're going to focus on the bonding in Chapter 9 and the arrangement of the atoms, the structures, and all that in Chapter 10. So pretty simple. We're going to be looking at bonding here in Chapter 9, and you can see the definition. We'll focus on three types of bonds. We'll actually focus on the first two, ionic bonds and covalent bonds. The key to these go back to what we talked about with compounds. If you remember, ionic compounds consisted of a metal and a nonmetal. So the ionic bonds are going to be the transfer of electrons. Covalent bonds, covalent compounds, molecular compounds, consisted of just nonmetals. So here we've got the sharing of the electron pairs. So ionic bonds, we're going to see those with ionic compounds. Covalent bonds, we're going to see with the molecular compounds. But again, throughout this, we focus on one aspect, and that's the octet rule. 8 is the magic number. And what that has to do, and you can see the statement there, the atoms, whether it's through a transfer of electrons, through a sharing of electrons, each atom wants 8 total for this. Okay, couple things. We're going to go through this quickly. I'm not going to go too quick, but things to remember with ions. The positively charged ions, hey, those are our cations. The negatively charged, those are our anions. Remember with the cations, they're from the metals, the anions from the nonmetals. And again, we talked about the formation, the gain or loss of the valence electrons with this. And again, you can kind of see the aspect here with that formation, the movement of the electrons. Here they're showing the electron configurations, and you can see that electron moving from the sodium to the chlorine and the change in the charge. Okay. The ionic bond itself is an attraction bond between the negative charge. That's what's going to hold together. And I like this statement here. Both of these happen together. We're going to transfer the electrons. We're going to attract the ions to each other. And you can see that here with the sodium and the chlorine. One of the ways that we can show the valence electrons and we can show the transfer is using what we call Lewis symbols. We talked in Chapter 8 about the number of valence electrons and how we can use the periodic table to give us the number of electrons. A Lewis symbol, basically the number of electrons that an atom has, valence electrons, that's going to be the number of dots on the atom. And you can see that here in table 9.1. Look at each of the groups. Look at the number of dots that each one has. They represent the number of valence electrons. And we can use this to show the transfer. Here's magnesium and fluorine. Magnesium, a metal, is going to lose both these electrons. Fluorine will gain enough to have one each, and you can see the movement of the electrons there. And the same thing with the sodium and the chlorine, that transfer of the electrons. We're going to skip ahead here a little bit. Okay, some things to keep in mind with the ions. The charges, again, we can go back to Chapter 2 to see that table of charges. Here is just a reminder of what we're going to see for the charges of each of the ions. The cations, again, the main group, they're going to lose all their valence electrons. And you can see that here with sodium and the configuration for sodium. And the same thing with manganese. Again, a skip ahead here. So again, we're going to lose the valence electrons. So we're going to lose the 4s2 electrons here. And that's what you see there for the charge of the manganese. The transition metals are unique. They can form more than one cation. And what happens? They'll lose the valence first, and then the d electrons. And you can see that with the iron here. We've looked at solutions, so this is an interesting thing about the colors of the solutions that we have. The anions, they gain enough electrons to get that full valence shell. Again, we talk about the octet rule. Hey, there's our 8 electrons right there. And you can see the configuration. Atomic radius, much like ionic radius, much like atomic radius, hey, it's just a measure from the nucleus to that outermost energy level, now with the ions. Here's something unique. The cation is always smaller, the anion is always larger. So we want to keep that in mind. Okay, covalent bonds. Again, these are going to exist between the nonmetals. They're going to share the electrons. One of the easiest ones that we look at is hydrogen. And here they talk a little bit about the energy and how with the sharing of the electrons, you get a much more stable, a lower energy molecule than if they're just the two separate atoms themselves. We can use a formula to show how the electrons are shared between the atoms. Two things we've got. The electrons between the two atoms, we call those bonding pairs. The lone pairs are the ones just on a single atom, not shared with anybody. Coordinate covalent, and you can see here, hey, both electrons are donated by one atom. And again, our octet rule is the focus. We want we want 8 electrons total. 3 types of bonds: single bond, double bond, triple bond. And you can see the aspects here. Keep in mind, all the nonmetals can form single bonds. The double bond, there's only 4, and it's covered up here, but it's carbon, sulfur, nitrogen, and oxygen. And then a triple bond, carbon and nitrogen. Keep that in mind as we're looking at the structures of compounds. With a double bond and triple bond, look at how the atoms are shared. And we can see, again, the Lewis dot formulas, and we even got these line structures for this. We talk about with covalent bonds the sharing of the electrons. The sharing is just kind of the quote, because some cases you have a polar covalent where it's unequal, a non-polar covalent where it's equal. And the difference between the two has to do with electronegativity. Every atom has this ability to attract electrons to itself. Figure 915 has the values of these electronegativities. This is a figure that you can go back to. And you can see fluorine has the highest electronegativity. Metals tend to have the lowest. And what we can do is we can look at the difference in electronegativity values to tell us if we have a nonpolar, a polar, or an ionic bond. And you can see the values there. So it's just a matter of finding our 2 atoms, doing the math, and see where it falls with the bond. And you can see, I'm not going to go through the example here. And again, we mentioned that electronegativity, and what we end up having is we can have these partial charges down here. And the partial positive, partial negative. The partial negative is always going to be on the more electronegative atom. Okay, the last part of chapter 9 focuses on now the structures. We're going to focus just on covalent compounds. So all of these have, nonmetals. But again, one of the compounds here, POCl3, look at how the atoms are arranged. You've got a central phosphorus and then chlorines and the oxygen around them. And the same thing with this chlorosulfonic acid. The central sulfur, look at how the atoms are arranged. So we want to write these electron dot formulas. You look at these steps, follow these steps. They don't change. Okay? Doesn't matter what your compound is. We always start by calculating the number of valence electrons. We write the skeleton structure. Our central atom is always going to have the lower electronegativity value. The only difference, hydrogen. Hydrogen will never be the central atom. And then you can see the rest of the steps here. So we're going to go through a couple of examples where you see this. We start with the sulfur dichloride. And again, you see what they start with. We add up the total number of valence electrons. So we're going to account for all 20 of these. We draw our skeleton structure. Sulfur here is the central atom because it has the lowest electronegativity. So we draw that, and then you see, hey, each of the chlorines, we give the octet, and then we give the remaining electrons on the sulfur. And as you look at these three examples, you're going to see the same thing happening with them. And I'm just going to go through the first one, the oxygen difluoride. Again, we count the number of valence electrons. We draw the skeleton structure. Oxygen's the central atom. It's the lower electronegativity. Note how the fluorines bond, each fluorine bonds to the oxygen. The electrons go around the fluorine, and then the remaining electrons go on the oxygen. And I'm going to skip through these real quick. You'll see the same thing with that. And the same thing with this COCl2. But here now what we've got is a double bond between the carbon and the oxygen. For polyatomic ions, we do take account of the charge. You will know what's a polyatomic ion. They're going to give you the charge. And again, if it's the anion or cation, you've got the thing that you can do with this. And again, here's the structure, PCl4 plus charge. It's a cation. So again, with the cation, you do the subtraction, and you get the structure. Delocalized bonding is very interesting. Look at the definition. It's spread out over a number of atoms, not localized. We can draw resonance structures. And one of the best resonance structures that we have is the carbonate ion. Because note one thing that you can see with the carbonate. Here's the double bond between the carbon and this oxygen. But I can also draw it where the double bond's here, or the double bond would actually be on this other carbon here. There are some exceptions to the octet rule. Most of them have too few. The majority, we have what we call the expanded octet. The key with this, they all exist in the third period. They all have a D subshell. Okay, so that's the thing to remember when you've got a central atom that can have this expanded octet, like phosphorus pentafluoride here. Note 2, 4, 6, 8, 10 electrons. And you see the structure, the model of this. But we still follow the same steps. We count up the total number of valence electrons. Note with, this should be fluorine, but note with the fluorine, they're going to multiply that times 4. Hey, we got 36 electrons. There's my central xenon, the bonds to each fluorine. We give each fluorine enough electrons to satisfy the octet rule, and then remaining electrons go on the central xenon for this. I'll let you read the rest. Bond length, bond order, look at the definitions for each one. With bond length, it's a math. Pick your two atoms, add the radii together. There's your length of the bond. Single bonds are always the longest. Triple bonds are always going to be the shortest. Bond energy, how much energy does it take to break that bond? And again, it's a math. Find your two atoms and just take that number. Okay, so I know this was really quick. Take your time as you go through the chapter, as you go through the quizzes and stuff, look back, read, and go from there. If you have any questions, please contact me. Take care.